All right, Math 5130. The purpose of this video is to demonstrate how to write the results from a one-way ANOVA. So we're using the body data set, and we're going to examine the mean differences for pulse across age. So you can see the first thing I do is I force age and sex, even though I'm not using sex in this problem. It's a good habit to get into. Just go ahead and force the categorical variables into factor status with R. Does it work without it? Sometimes it doesn't. Let's just be safe and always get in that habit. Report the sample size. I actually forgot to do that at the top, but you can see down at the bottom I do the length for the dependent variable pulse, and it's 300. Next thing I do is report the mean and the standard deviation for pulse as the variable, not over age, but just for the 300 participants. And you can see that I've accessed all this just using summary pulse, where I get the mean, the median, first quartile, min, max. All that is reported right here. The standard deviation is not reported in the summary output, so I get that with SD command. The next thing I do is look at a box plot. We can see that there's one outlier. I've demonstrated this multiple times, how to do histograms and box plots, so I don't do that in this video. Next thing, I switch gears to the categorical variable. I just pull out the one that has the highest sample size, which is 127, and the highest percentage, 42.3. You can see that I get that by setting up the table for age. I just called it a table because I'm not that creative. Here are the counts, 113, 127, and 60, which are reported right here, along with using the prop table command, which gives me the percentages. Next thing we do is we switch gears to the ANOVA. So we're now starting to take our sample data and generalize to all people, or at least the population to which we feel comfortable generalizing. Is there a mean difference in pulse? Is the mean difference in pulse significant across age group? So the result was significant. You can see right here I ran the ANOVA, called it model. Then I ran summary of model to get the table, the sum of squares, mean squares, and all that. Again, we don't go into that in this class because it's not appropriate. So I report that. So we're in the F distribution, as I talked about in a previous video. Degrees of freedom are 2,297, which I get from this output right here. The F value is 3. Actually, that should be 3.90, rounded correctly. And our p-value is statistically significant at the 0.05 level. This indicates there is a statistically significant difference for at least two groups. Could be the 18 to 39, 40 to 64, it could be whatever. So now we'll get into the post hocs later. Small effect size was observed. Remember, the effect size can be just kind of crunched out by taking the sum of squares for our independent variable age divided by the total sum of squares. So to get the total sum of squares, I have to add these two numbers, which I've done right there. And you can see our effect size is 0.026. So that's a small effect using the metrics that I presented in the previous video. So then I want to dive into reporting the pulse rates across each age group. And that's really easy to do in R. Just use the tapply command. So I put the dependent variable first, the independent variable second, or the quantitative variable first, the categorical variable second, and the statistical, the descriptive, in the mean or the standard deviation in this case, next. So I can see that 65 and older was the smallest, and the standard deviation was 12.86, and I just report that for the others. Since the ANOVA was not significant, we need to run a post hoc analysis. And I did that right here. And we have tunnel vision when we create this, in that we look to this p-value, which is adjusted because we're conducting multiple tests. We have this inflated type 1 error rate I discussed previously. So we have to control for that. And Tukey is brilliant at controlling for that. So we find that there's only one pair that's statistically significant. It's the 40 to 64 age group with the 18 to 39. So I report that, I report the difference, I report the confidence interval, and I report the level of significance at which it's statistically significant. Then I come into table 3 and report the pairwise comparisons. Now, this can get pretty messy if you have, let's say we have a categorical variable with 6 or 7 levels, then you could get into a lot of pairwise comparisons. But you know, it's just one of those things you have to just type it out. Table 2, pulse by age. And notice I've reported the means and standard deviations for pulse across each group, each level, if you will, of the independent variable. Reported my degrees of freedom, test statistic, and the p-value, or the level at which our p-value, our test is statistically significant. So if I did make any typos, this should be pretty straightforward. Next thing I do is I shift gears and move into the assumptions for the test. First assumption is we need to test normality. You can see that we fail that. I'm not concerned with it because, again, as long as our sample size is 30 or larger, we can revert to what we know from sampling distributions. Again, beyond the scope of this class, but again, no concern. Now, if we had a small sample, this may result in me wanting to switch gears and do a non-parametric test. More about that later. But again, large sample, 300. All of the, so we have 113, 127, and 60. So all the sample sizes within the groups are greater than 30, so I have no concern with that. But nevertheless, we still want to report this. And Levine's test, which I ran right here. First time I ran it with the default of center being the median, so I didn't want to do that. So then I ran it correctly with the center being the mean. And you can see that there's no threat to, no concerns with the equal variance assumption. Again, the null hypothesis for the Shapiro-Wilk test is that the distribution from which our sample data was collected is normally distributed. So we reject that here, determine it's probably not normally distributed, which is really surprising to me because when I examine this box plot, I see a relatively bell-shaped and symmetric distribution as I think about smoothing that thing out. So I was a little bit surprised by that, but you know, it is what it is. And the result of Levine's, again, no threat to equal variances. And it doesn't surprise me because when I look at the, well, let's just look at the variances. So if I take, let's go, I can use the up arrow. And let's just come in and look at the variances here. And you can see the variances are pretty close, 150, 130, and 165. So again, these are sample variances. So we're making a statement about the populations from which these sample variances were collected. So it's not surprising to me that we can move forward with assuming the equal variance assumption. In other words, that these data came from distributions that were normally distributed. All right, that's it for this video. Next video, I'm going to dive into StatCrunch and demonstrate how to make these calculations as well. Take care.